So far in this unit, we've looked at how to calculate delta H in two ways. We've used bond energies and we've used calorimetry experiments in order to find the delta H for a given reaction. In this lesson, we're going to look at the final two ways of calculating delta H. We're going to use Hess's law and we're going to use heats of formation. These are connected to one another because the heats of formation formula that we will use is really a simple application of Hess's law. Hess's law uses the fact that enthalpy is a state function. And you'll remember that enthalpy being a state function means that it's the initial and the final states that matter, the beginning and end that matter, and the pathway that we take to get from the beginning to the end is irrelevant in terms of calculating the delta H. If we look at this example here, we've got two different pathways to the same reaction. Reaction 1 and reaction 2 are actually two steps to complete the reaction that's discussed in reaction 3. So let's look at this for a minute. Sodium hydroxide, a solid, dissolving. The heated solution for this reaction is negative 43 kilojoules. So 43 kilojoules is released in this process. The reaction between sodium hydroxide solution and hydrochloric acid solution is an acid-base reaction with a delta H value of negative 55. These two reactions are really added to produce this final reaction, but we could do this third reaction on its own. So in an experiment, we could do reaction 1 and reaction 2 and find their individual delta H's. We could then also subsequently find the delta H for this reaction, where we react solid sodium hydroxide with aqueous hydrochloric acid to produce the sodium chloride and water. The delta H for this reaction is negative 98. If you look at the values, this plus this is equal to negative 98. So really, these two steps are equal to this one-step reaction. And if we look a little bit more carefully, we can see that when we add these reactions, the way that we've learned in the past, okay, they add the way that we would expect. And what this is showing us is that the pathway that we take to find the delta H does not matter as long as the overall is the same. Okay, so when I add these two reactions, what ends up happening is the sodium hydroxide aqueous ends up simplifying, and what I have overall is a reaction between sodium hydroxide solid and hydrochloric acid to produce the sodium chloride and water. So reaction 1 plus reaction 2 is equal to reaction 3. And the delta H of 1 plus the delta H of 2 is equal to the delta H of 3. And this is because delta H is a state function. If we think about it even closer, we can see that this reaction really occurs in these two steps. So when we react solid sodium hydroxide with a hydrochloric acid solution, what ends up happening is the sodium hydroxide dissolves and then the dissolved sodium hydroxide reacts. Okay, so no matter which way you look at it, reaction 1 plus reaction 2 is equal to reaction 3. So if we can add 2, 3, 4 reactions, we can find the delta H of the overall reaction. And perhaps what you see developing here is a skill that we've already used before where we combine reactions and add them to produce a goal reaction. We manipulated the initial equations in order to make them add up to a final reaction. We did this when we were working with K, and we wanted to find the equilibrium constant for an unknown reaction. We manipulated some initial reactions and then added them to equal our final reaction. And there were rules associated with the manipulations that we did. Our discussion below shows us that when we add reactions, the delta H's simply add up. This is different from the equilibrium constant rule, so you need to keep that in mind. Now, the other manipulations that we do when we're performing Hess's law or applying the law of additivity is we could end up needing to flip a reaction around. If we flip a reaction, so for example, if we wanted to flip this reaction around, it would change the sign of the delta H because a previously exothermic reaction, where energy is a product, would become an endothermic reaction where the energy is a reactant. These are a little bit more intuitive than the rules we had for the constant K. The other manipulation that we might need to do is to multiply a reaction by some value x. To understand what the effect on delta H is, we need to remember the relationship between the delta H and the balanced chemical equation. The delta H for a balanced chemical equation is consistent with the mole ratio in the balanced chemical equation. So for example, the negative 43, the 43 kilojoules released occurs when 1 mole of sodium hydroxide is dissolved. So if we changed this and had 2 moles of sodium hydroxide dissolving, then the amount of energy that we released would be double. Because whatever we do to the equation, the same is going to apply to the delta H value. So this kind of question will look familiar. We want to find the delta H for a particular reaction using a certain set of reactions that have known delta H values. So you'll recall that we look at our goal reaction and we make decisions about what manipulations we need to make on the given reactions. Ultimately, we want 2NH3 in our final reaction. So when we look at the second reaction, which has a 4NH3, that tells us that we're going to need to divide that reaction by 2. Because the O2 is found in all of the reactions, it's not going to be all that helpful in making decisions about the manipulations we need to make. So we'll skip over that one and look at N2O. For N2O, we need it to be a product with a coefficient of 1. So this final reaction needs to be manipulated by dividing it by 2 and flipping it. To get the 3H2O as a product, you'll see that we need to divide the second reaction by 2, and we've already made that decision. At this stage, we've gone through all the reactants and products, and we haven't made any decisions about the first one. And rest assured, they're not going to give you a reaction that is useless. So what we're going to do is just leave that and see how it's going to be useful to us in a couple minutes. Okay, so we're going to write out what we have. We've got 2NH3 plus 5 halves O2, 2NO plus 3H2O. And with these, you'll notice that the states are given. Okay, it's really critical that we keep the states in mind because only compounds with the same state will be able to simplify one another. All of these are gases, so I don't need to write out the gases, but I do need to constantly be keeping in mind the states of the reactants and products. Because I divided this reaction by 2, I divided all of the coefficients, and the delta H also needed to be divided by 2, because if I use half the amount of moles, I'm going to release half the amount of energy. But the sign didn't change because it remains an exothermic reaction. For the third reaction, I need to flip it and divide it by 2. So I get 2NO2 goes to N2O plus 3 halves O2. In this case, I need to change the sign and I need to divide it by 2. Now, a few things to note when you're dealing with these. The signs when you're doing the computations are really important, so I would recommend that you are deliberate about the signs so that you don't forget them. And what you're also going to find is that you're going to end up with fractions for oxygen. Okay, you can put that in a decimal if you want to put that as 2.5 and 1.5, that's fine. Now, if we tried to add these up, it would not add to this final reaction because we have some extra materials that actually need to be removed. And that's what this third reaction is going to help us to do. You'll see that there is NO in this reaction, but there's none in the final reaction and nothing in this second one to cancel it. But if you look to the first reaction, you can see that if I just leave it, 2NO plus O2, that's going to simplify the 2NO. And it's also going to simplify the 2NO2 that I've got here. So this is one of the more challenging additive reactions involving an extra reaction that's used to cancel things out rather than to actually obtain the reactants and products that you want. Okay, so we can see the 2NOs simplify, the 2NO2s simplify. And the oxygens here, we've got 7 halves on the left-hand side and 3 halves on the right-hand side, which leaves us with the 2 oxygens that we're supposed to have. Okay, and as expected, the reaction adds up to our reaction that we were trying to determine. And when we take these delta H values that we've worked on, we're going to find that we get a value of minus 552.5 kilojoules. So this is how you find the delta H using Hess's law. And I encourage you to pause the video and work on this problem. The delta H that you should obtain for this reaction is 226.7 kilojoules. The final way that we're going to find the delta H for a reaction is using something called standard heats of formation. Before we look at how to use standard heats of formation, we need to first look at the definition of standard heats of formation and understand that. The symbol for heats of formation is delta H naught F. Okay, delta H being the enthalpy, this naught symbol, or this little superscript of an O, means that the experiment is carried out at standard conditions, which means 25 degrees Celsius and 1 atmosphere. And the little left stands for formation. Now this is thermodynamic data, heats of formation. So you find the values for the standard heats of formation in your textbook. Okay, at the back of your textbook in the appendix, there is an extended list of compounds and their appropriate delta H naught Fs, which you may need to refer to. On page 253, there's a simplified list of some key compounds. Now what these values are is the amount of heat that is absorbed or released when 1 mole of a compound is formed from its elements in their standard states. This is a very specific definition, and it's one that we need to evaluate wholly. Okay. A few important points here. We are forming 1 mole of the substance. It's going to be an exothermic or an endothermic reaction. And the element is formed, the substance is formed from the elements in their standard states. And what we mean by that is it's formed from the elements in their regular state, so liquid, solid, gas, whether it's diatomic or not, at these conditions, at 25 degrees Celsius and 1 atmosphere. So if you look at these examples here, we've got H2 plus half O2 going to H2O, and this is a heat of formation. We're forming 1 mole of liquid water from its elements, so from hydrogen and oxygen, in their standard states. So hydrogen being a gas and oxygen being a gas in its standard state. Now what you'll notice with these reactions is that we often need to use fractions because we cannot change the coefficient in front of the product. We're always forming 1 mole of the substance. It's very specific. The second one is another example of a heat of formation reaction, this time for carbon dioxide. It's formed from carbon and oxygen gas, and it's got a heat of formation. If we look on the chart, that is the value for the heat of formation. This third one, producing carbon dioxide from carbon monoxide and oxygen, is not a standard heat of formation. It doesn't follow the definition. although we're forming 1 mole of the substance, we're not forming it from its elements in their standard states. A few things to note about this chart. There are lots of substances that have values of 0, and what you'll notice is that these are all elements. An element is not going to have a heat of formation because an element is already in its standard state, so it can't be formed from another element in its standard state. Another thing to notice is that the state, whether a substance is a gas or a liquid, so for example with water, the state matters, so we need to pay careful attention to that when we're recording values from the table. So there's a few things that we need to be able to do. We need to be able to write thermochemical equations for the standard heats of formation, and we need to be able to identify whether or not we've got an appropriate reaction. And then we also need to be able to calculate a delta H value for a given reaction. So first, we'll look at how to write out the reaction for the heat of formation of pure acetic acid. In the short table that I've given you, you're not going to find the value, but if you look in the appendix in your textbook, you'll find the value for the heat of formation of pure acetic acid, which is a liquid, is negative 487.0 kilojoules. When you're writing reactions for these, you're going to want to start from the product side because, by the definition, we're always forming 1 mole of that substance. In this case, our acetic acid is a liquid. The elements that we're going to use to form it are carbon, hydrogen, which is a gas and it's diatomic, and oxygen, which is a gas and it's diatomic. So you write out the elements, and then we need to balance this equation, keeping in mind we cannot change the coefficient in front of the product. So here we've got 2 carbons, we've got 3 hydrogens, and we need 1 oxygen. And there we have a balanced chemical equation, the thermochemical equation for the heat of formation of acetic acid. Now we can use the table values in order to calculate the delta H for a given reaction. And what we're going to do is first apply the formula that we're given, and then I'm going to show you why the formula is simply an application of Hess's law. If you've got a given reaction, some compound A plus some compound B, and it's reacting to form some compound C and some compound D, to find the heat of this reaction, what we're going to do is take the sum of the heats of formation of the products, and we're going to subtract the sum of the heats of formation of the reactants. So let's apply that formula to this reaction. I want to find the delta H of this particular reaction. I need to take the sum of the heats of formation of the products. So if I look on the table for N2O, it's 81.56. I need to add that to the heat of formation of 3 moles of water. Okay, so when you're taking the sum of the heats of formation, you need to take into account the coefficients. Then we're going to subtract the sum of the heats of formation of the reactants. So we've got 2 NH3, so 2 times negative 46.3. And plus 0, because oxygen is an element already, it's got a heat of formation of 0. Now, as you can see, the actual computation is going to be a bit of a mess, so you need to be careful with the signs, and I would recommend that you double check your calculations when you're doing these. Okay, when you do the math, you get negative 551.24. If you look back at the first example that we did, this is the same reaction, and we get the same value within reason. We're off by about 0.5 for the delta H. So you can see that this formula and using the heats of formation gives us the same value as a longer Hess's law example. Okay. We're going to look further into this though and prove that doing this calculation, so taking the heat formation of the products and subtracting the heat formation of the reactants, does give us the delta H for the reaction and is simply an application of Hess's law. We're going to do that by breaking down this reaction into a series of heat formation reactions. What we're going to do is look at the heat of formation reactions that we can for this reaction. So for NH3, for N2O, and for H2O. Okay, and this is H2O gas that we're dealing with here. So if you take a minute and practice these, okay, which is a good idea, writing out the reactions, okay, with the appropriate fractions. And we get the heats of formation values. So these are the appropriate heats of formation reactions that would apply to this particular overall reaction. Now if we take these reactions and we apply Hess's law, use these reactions to find the delta H for our goal reaction, let's see what happens. Let's make the decisions here. We want, in our goal reaction, to have 2NH3 as a reactant. So we would need to take this reaction and we would need to flip it and we would need to multiply by 2. The second reaction doesn't need to change because in our goal reaction here we've got 1 and 2O. Okay, I've just noticed something here. This should be plus and this should be an arrow. Okay, so we want 1 mole of N2O. So this reaction doesn't need to be changed. We want in our goal reaction to have 3 H2O. So what that means is that we need to take this reaction and we need to multiply it by 3. Now if you'd like, you can stop, take these reactions, apply the changes, and ensure that they do in fact add up to this goal reaction. What we're going to look at is not the computation of that because it will work if we do that. We know Hess's law and how it works. What we want to focus on is how these decisions we've made are actually the exact same thing that the formula asked us to do when we took the heats of formation of the products and subtracted the heats of formation of the reactants. Okay. What we did here was we left the 81.56 on its own, and we need to leave the negative 241. The sign remains the same, but we need to multiply that one by 3. Okay. And then this one, the NH3 being a reactant, was the one that we needed to flip, and that caused the sign to change. So anything that is a reactant needs to be subtracted. Okay, and there was no part of oxygen. So what you can see here is that the decisions we made are the same that the formula asked us to do directly. Anything that we wanted to be a product came first and remained the same. It didn't change its sign, but it was multiplied by its coefficient. Anything that was a reactant needed to change its sign, and it was also multiplied by its coefficient. So that shows you that our formula of taking the heats formation of our products and subtracting the heats formation of the reactants is simply an application of Hess's law being applied to the heats formation. You don't need to be able to reproduce this proof. Okay, but hopefully it gives you comfort in knowing that this formula, heat's formation of products minus reactants, does actually work. What we've done is we've accomplished studying chapter 6, and we've looked at finding delta H in 4 different ways. So we've looked at bond energies, calorimetry, Hess's law, and heats of formation. For calorimetry, we broke out into 2 different types. We had heats of reaction and heats of solution, or heat of dissolving. At this stage, we're going to pause in our topic of thermochemistry and we're going to discuss kinetics. And so it's really important that you apply yourself and do the practice that you need on this topic because it is going to be important later on when we revisit thermochemistry.